I'm actually one of you. My master's degree work was in instructional technology at Utah State University, and that's what I did. But that quote there, I ran into it a few months ago, and I thought, you know, I taught high school for 20 years, and that absolutely describes about everything that I did as a high school teacher. I could have them read, and I could have them watch, and then I would know they wouldn't learn. I was pretty good at that. For about 10 years, I understood really good that I could have them read, and I could have them watch, and I could also see that they didn't learn. And then all of a sudden I realized that there had to be something more than that, and that was that they had to engage themselves. Their minds, their hands, everything had to engage. And then I still didn't know if they learned, but their test scores went up. So I don't know what that's a reflection of, but they got better at it. So today I'm going to give you a chance to engage in that kind of a lesson. And I actually just tried it this morning for the first time, make sure that it would work. I'm not sure what I do that works sometimes. But this is my high-tech equipment this time. It's a piece of sewer pipe, okay? And I have nice things in here. This is just a block of wood. And the block of wood is because I made, you guys know what a pile driver is? You know, if you've ever pounded electric fence posts, that's a form of a pile driver, or watched them tear down buildings or something else, that's a form of a pile driver. Well, I made 3 pile drivers. One's 10 centimeters, one's 20 centimeters, one's 30 centimeters. Okay? That's what they are. And they're actually full of rock salt. That's the only thing I can find real quick today that would make them kind of heavy. And I wonder how they package things. I'm always wondering how they learn how to package things so they don't get broke. So I thought, you know, if I took it, they're empty, the can. If I took a pile driver and I'll do it with my spine.
It's over on the top of
This
this.
is the most important thing I found. 70 cents. You need to know how much things are. I'm going to go in, no, I'm going to put it right here. I'm going to put this in at 75 centimeters, that's marked, close to 75 centimeters. I'm going to drive the pile down into the 75 centimeter spot. Then I'm going to pick it up. Your ceilings are low in here too. Okay. Oh, no, you can do this. Maybe, well, we're going to have to go up. It's just how life is in these backwoods. I might move that in a minute, okay? So, what we're going to talk about is the ability to get hurt. That's what we're going to talk about today. Different things have the ability to hurt you worse than other things. In the process that I have here, I have the little one in, there's this one and this one. Everybody knows that if I was going to get hit, I'd rather get hit with this one. Does that make sense? Mm-hmm. So you just pull out the thing. It hits a can. There's a chair. You got to take out that.
We just have to move that.
Oh, I got it. Look at
Nice.
that. Look at that. Okay. Set that can on it. We'll just set it right here. We'll just set it right here because I think we can get something from it. So let's take another can and put it here. And that was at 75. So let's go 75 more would be what? 150? Yeah. Yep. 75 and 75, 150. So we would say that this has more ability to hurt now, right? More ability to hurt. Okay? So now we have more ability to hurt. So let's look and see what happens. Ooh. Okay? What's 175, 150, what, 225? Where's that? One more hurt to go. Pick that up. Okay. This is actually really good. It just stays right there. We'll put this right here. Look at this. Can you see the more hurt? You see one hurts more than the other? You see that? Okay. More hurt. So let's go up again. So you take the little pile, go up here, put it on here, come back down. Almost to my ability to hurt. Oh. Okay. Then we have that. So we have the third can. Now look at those. Are those? Have you ever seen a graph? Okay. You guys know what bar graphs are? This is a can graph. Okay. This is a can graph. So that's the little pile driver. Let's see what the difference happens when we go up to the bigger pile driver. Okay? We jump up to the next level, and 75 centimeters again. What you see in here?
How much bigger?
What?
How much bigger?
It's about a third. Because it's 10,
This is a third heavier?
10, 20, and 30 is what their lengths are. And I have more cans here. Okay. I found out that I have a secretary that hides this stuff underneath her desk. It even keeps the cans. Okay. Now we're actually at the same place as this one, right?
Yeah.
But we changed something. We made something that's a little more massive. So we pull it. So we take it out. Oh man,
You got it finished.
something happened there. Okay, so that one's this one now. Okay, so now what do we need to go up to?
150.
150.
I think you have a pretty big soda pop now.
I don't. I just stole them from her desk. I honestly, I went in looking for them, and she had a whole bunch of cans underneath her desk. We might find out that not all cans are created equal too. But we'll see here. There's the middle one. Okay, that'd get pretty good. That one, I think that's a bad can. I think it's in an all, oh, good stuff. Shasta. Okay, and we're from the 225, right?
225.
Well, you gotta write it down anyway, just to make it easy. 225. Same thing. Put it up in here. Bring it back down. See how we do at 225. Oh.
That's nice.
The can graph's gonna work pretty good, I think. Okay. Looks like that Shasta's pretty tough, but it went down. Okay. So all we have left is we need to graph 3 more data points. 3 more data points. Okay, so 75. Normally I would just tell you students to do this, but I need to get it.
Don't want anyone to hurt themselves.
That sounds like it's got a lot of hurt in it. Well, that's another can.
Trained professional.
Okay. There we go. Big, 3 times longer. Okay, so now we're over to this one. Okay, and we're gonna do 75, 125, right?
150. 150. Which one?
50. Oh, no can there yet. 150. Okay, I made my clothes hurt. Just listening to it. Okay, there's 150. And the last data point we're going to use today. 5. Big pile driver.
You didn't have a chance.
Pretty good. Okay, pretty good. Now, you gotta make this go up. How do you do that? There's power over here. Okay. Now, what you have is a really nice graph. You have a really nice graph there, and if you look real close, some of these cans, I wish I would used all the same cans so I knew it wasn't can problems. some of these can't see these two, maybe some on the ends. They're really close to the same squishness. So let's look at it just from a point of view. We're looking at the ability to hurt. And that's what we're going to call this, is the ability to hurt. Okay? The things that we've varied so far, we did mass. We have one that's one mass, one that's two masses, and one that's three masses. Okay? That's the, well, the other one's still in there. But the, oh, here it is. There you go. One mass, two mass, three mass. Okay? What's the other thing we varied? Well, we did height. So we did one height, two heights, and three heights. Basically, we did them all 75 centimeters. We'll just call them heights right now, okay? Because we just varied them. And if we look at those two things, if we were on the International Space Station, would this experiment work? Why?
Ceilings aren't tall enough there.
Probably, that's probably good. We could do a shorter tube. Okay?
They drink Pepsi.
There's actually almost as much gravity at the International Space Station as there is here on the Earth.
But it's affecting everything.
But on the at the International Space Station, everything's falling. And so it won't fall because everything else is falling also. And that's just a physics kind of thing. Don't worry about that. But that's why it won't work there. If we were on the moon, would it have the same hurt as it has here on Earth? So the other variable here is how fast you can accelerate it, right? So that's gravity. So we'll just assume that we know what gravity is. It's the same on all of these. So if we multiply these out, I get 1 times 1 is 1. I get 2 times 2 is 4. I get 3 times 3 is 9. I did this wrong, by the way, because I need to do this way. Where's your eraser? Right here. I need to do it this way. Okay. For the one mass, I have 1 height, 2 heights, and 3 heights, right? For the 2 mass, I have 1 height, 2 heights, and 3 heights. And for the 3 mass, I have 1 height, 2 heights, and 3 heights. Okay, that's what I have. So 1 times 1 is 1. So the ability for this one to hurt is 1. Does that make sense? 1 mass times 2 heights is what?
2.
You guys are pretty good. Okay. The ability to hurt is 2. 1 times 3, the ability to hurt is what? 3. Okay? So 2 times 1, the ability to hurt is what? 2. 2 times 2, the ability to hurt is what?
4.
4. 2 times 3, the ability to hurt is what?
6.
6. Look at this. 1 can at 2 heights should be about the same as 2 masses at 1 height. Can we find those cans? This was 1 can at 2 heights, 2 cans at 1. Okay, and remember I told you that can looked like a wimp? I think that's the problem. But those should be about the same. That's pretty bad. Let's see if we can find another one. 3 heights, 1, that's 3, right? 3 and 2 is 6. Oh, we got 6 is right here, right? So the 3 at the middle, which one's it? Pick it out. 3 at the middle, that one right there. It's the Shasta, isn't it?
No.
3 heights at the middle. Is it the Shasta? And this one.
No, but that's
It's these two, isn't it? Look at that. It's these 2 cans. You see that? It's those 2 cans. They're the same. So the ability of hurt comes with 2 things. What are they? That we know of already. Mass and height. That's the ability of hurt. And the last one we don't talk about is gravity. Okay? Is G. Okay? Whatever the acceleration is of it, but it's all the same here. And so we know how to calculate how hard something will hit. And even in this case, I think I have 1 weak can, but in this case, the pattern really shows up with those 2 different cans. They're basically the same thing. Okay? Now, when people package things, do you think they have to worry about making sure they don't get broken in movement, okay? And so they don't get hurt, and so that's what we're going to do. We're going to see if you can package something so it won't get hurt, okay? That's pretty simple. Because the thing you're going to package is a single Pringle potato chip, okay? So your job is to take out one single Pringle potato chip and build a package around it so that we can put it here. We don't want to mess around, so we'll do big guy. Okay? We'll do big guy from 2 meters, just right here. We'll do big guy from 2 meters.
Sweet.
Does that make sense? And it has to be able to fit in the tube, just like this. We still have to be able to set it over it. Let it go, and then we'll see if you can package a single Pringle potato chip so that it doesn't get dusted or busted, or whatever you want to use. Whichever, some of them will, I'll show you. Sometimes we could call it dusted. Okay? You put a single Pringle in there, and you use, well, we don't have to use any of the big ones. Okay.
I'm sure there's a rule against the big one.
No.
You hit the nail, you didn't
Got
hit
your
it.
nail.
Sorry, sorry.
My spine, where'd my spine go?
It was pointing at me.
I love my spine. And now, for a science teacher, what I would tell you just happened was we're just developing the idea of potential energy. And potential energy is actually mass, height, and gravity. That's what it is. But I want the kids to think of it as how energy is kind of how much it could hurt something when it comes to potential. So you do this, okay, and you look down there, and we didn't do a very good job packaging that Pringle, okay, and so that's kind of the process there. Now, the hard part of it is all you get is what's in these boxes, unless you can find something else in the trash can, you know.
Got an extra can? Or?
I got cans. Okay, but in these boxes, I'm just going to put them right here, because you guys spread yourself out. There's just junk. And it's mostly just junk out of the kitchen. Okay? It's just your kitchen sink kind of project. Okay? And that's what you have there. So,
Any team can pull out of any box.
oh, you can use anything you can find in there. And how I usually do it, there's this thing right here. We're going to base how good your project is on how light you can make it. So let's say we had a great big grand prize or something. It would be whoever's Pringles survived with the least amount of mass. Because shipping stuff, they want them in light containers to protect them. Like, you ever think about an egg carton? They do a really good job of protecting eggs, by the way. There's probably a reason for that. But are they out of heavy stuff? Absolutely light stuff. Okay? So if they ship your computer to you, they probably would like to be able to protect it, but in a light amount of material, because that saves them money in shipping and in building. Does that make sense? So this scale will let you measure it. When you get ready to drop, all you have to do is write your name of your team or group you're working with, or your individual. You can have a cipher group if you want. You can do it all by yourself. Okay? And just write up there, write your mass, and we'll check it. Okay? All I can say is have fun. We have to do this in about 25 minutes, 20 minutes. 20 minutes. Can't use it, and you can't use the tape dispensers.
What? The core thing? You
No,
can't?
no.
I thought you said.
I just lied. Are you gonna use it?
That's a good idea.
Just like something
You should try it too.
Here, let's just drop one of those on here and see run it by itself. Just see.
They did try to make it more than air. Is it gonna smash on the bottom?
Did you guys take the whiteboard?
I don't think so.
As far enough
No, it doesn't have
to
the big
fit
ones.
all of that in there. Maybe if I get, I'll try to get another set of those just to see how tall it is, and then we could. So what about like putting other marshmallows in the top of here?
Yeah, that's a good idea. Let's try that. Yeah, and then let's try.
Okay, go ahead and see what you got. Did it crush?
It did.
Here we go.
I'm still curious how this all works out. Grab some marshmallows and try it.
Edible tape, right?
55 grams.
Pretty heavy.
Man, it locks in too.
Yes!
Bounce isn't a good thing in physics. Same design.
More efficient.
Here we go. Somebody's got to survive.
You know, they really just need to learn how to put things on their touch.
Got it. Sounded good. Grab the thing.
Oh, it's smashed. And do a couple pieces.
You ready? Here we go.
33 grams.
So hard.
It sounded tasty.
Go ahead.
Wow.
My breaker tipping over.
Put it in the middle.
Oh, we have to dig it out of the cereal.
It's in the Cheerios? Oh, chips in the Cheerios. Excellent.
Yeah, Cheerios survived.
They're still there. The chip protection.
Maybe we need marshmallows on the bottom.
I've looked for that. Bouncy. Oh, okay,
Airbags.
It's like, oh, they're popping a couple of.
Yeah. It wasn't very massive, but it did have some height, right? Maybe it was Clover Club. That gets everybody so we can start talking about things like mass, gravity, and height. Okay, so everybody in the room now has had an experience with mass, gravity, dropping, except for the one we didn't want to play. Everybody's had an experience with it, and we can look at it. There's a name for mass, gravity, and height. It's called potential energy. And if we look at the potential energies of these, the one mass, it had 10, 20, and 30. The two masses had 20, 40, and 60. These are joules, or amount of energy. And the three masses had 30, 60, and 90. So we had two that are 20, and that was the two small ones that were crushed, or the tallest ones that were crushed. We had two that were 30, that was the one Coke can crushed. Then we had two that were 60, and those are the ones that ended up being the same size, because even though they were crushed with different masses from different heights, they actually still had the same ability to do something. And the ability to do something is called work. Okay? So the energy had the ability to do work on the object. Now, the next question would be, which ones hit at the highest speed? You already know. You really know.
The shortest ones.
The highest one hit with the... But did the mass have anything to do with which one hit with the highest speed? And that's an interesting thing that's really difficult, because we can now go, we've learned about potential energy now, and I'm doing this real quick, is mass, gravity, and height. Conservation of energy says that energy is neither created nor destroyed. And so either it's all potential, or right before it hits, it's all kinetic, it's all moving. And kinetic energy is where I would take you next to 1/2 mv squared, 1/2 times the mass and velocity squared. And then interesting things happen. If these two things are equal, they always have to, the total of those two things always have to be the same. Then I can put mgh equals 1/2 mv squared. And if you look at it, it doesn't matter how much mass, whether it's the one mass, two mass, or three mass, they all are gonna go the same velocity from the same height. And my kids that I work with struggle with that. That the least massive one, this one from 2 meters, will actually be going as fast as this one from 2 meters, but they know this one does more damage, a lot more damage, and they can see it with just, even just the little pop cans right here. They can see which one did the most damage. And then that comes into it. Why does it do more damage? Well, it's because it does have more mass. And that's Newton's first law, that a mass that's moving wants to keep moving. So lower mass doesn't want to move as much as big mass. So now I've circled them all the way back to another thing we've already taught previously, which is why it's inertia, Newton's first law. And so I give you my PowerPoint. Most of you participated. Welcome to the electric fence generation.